also on the homework. This is the main implementation question on the homework. Okay, let's go back to optimizing objective functions, which will be what we're doing for the vast majority of this class. So we have training set, model class, loss function, and our goal is to minimize the loss function. Right? And for this lecture, we'll just be focusing on squared loss, because it's the simplest loss function. It's just quadratic. And next Tuesday, we'll be talking about other types of loss functions, such as the ones used in support vector machines and the like. And thank you, Bill Gates. Don't send real people. Alright. Don't you love it when Windows products crash? Alright. You know, I actually meant to migrate to Keynote, but then I got too lazy, and now this happens like once a month. I'm sorry. I'm going to apologize for it before. Okay, so the simplest thing to do when optimizing an objective function, especially if the objective function is differentiable, is to use gradient descent as the optimization algorithm. Right? You just take the derivative, you move in the, it's a minimization problem, so you move in the negative direction of the derivative. And for this lecture, we'll just assume that the loss function is squared loss, and we'll talk about the loss function in the next lecture. So, for squared loss, and I covered this in the last lecture, but I'll just cover it again for those of you who, it's been a while since you've taken multivariate calculus. So you have the loss function. You want to take the derivative, the partial derivative of this loss function with respect to the weight vector, also known as a gradient. And this loss function is, decomposing the summation over every training example. By linearity of differentiation, you can move the partial derivative or the gradient inside the sum. The loss function is squared loss. So by applying chain rule, you get this. And now you're taking the gradient of this with respect to your weight vector. And the model class is linear, right? And so this, again, using this fact and the chain rule again, we get this. So this is literally the gradient. This is literally the gradient or derivative. I'll use both interchangeably for squared loss on a training set. And so just remember this. Well, I'll usually use this notation for simplicity because it's cleaner. It's more generic. If it's not squared loss, you don't get something that looks exactly like this because the use of squared loss was in this step. So I'm going to stick with this step for most of this rest of this lecture. But internally, you can think of this, which is an explicit formula that you can implement for your homework. Although for homework, you have to implement something slightly different. So don't just copy this. You'll get the wrong answer. Okay, so this is how gradient descent works. We initialize our initial model. So the weight vector is 0 and the bias is 0. And then we do some loop, right? And in the loop, we take the gradient with respect to our parameters that we're updating of our current model. So WT and B sub t is a current model. And we compute the gradient, and then we make an update. That we update our model in the negative direction of the gradient because we're doing minimization, not maximization. And we do the same for the bias term. And I didn't show the derivation for the bias term, but it's analogous. And this eta thing is what's called a step size, right? It controls how big of an update you do. Right? If eta is large, then you do a large update in the direction of the gradient. If eta is small, you do a very small update in the direction of the gradient. And this is gradient descent. So, the only thing left, there's only two things left to do if you want to do this. One is to choose the step size, how to choose it, and one is when do you decide to terminate this for loop. And yes, early stopping by validation is a valid answer. There are other possible choices too. Okay, so how do we choose the step size? Let's just imagine a very simple optimization problem here. The loss function is simply the squared loss of 1 minus w. So w is a one-dimensional parameter. We're optimizing over a one-dimensional model. And the loss is simply the quadratic of 1 minus w. Right? So a single training example, a single feature, and the label is 1. Right? That's what this is. So the gradient of the loss function with respect to w is just negative 2 times 1 minus w. Suppose the step size is 1, and suppose we started at 0. So the gradient, points in this direction, right? That's the slope. That's the slope of this loss function. So in the one-dimensional case, it corresponds to the slope. And so if we started at w equals 0, that's the slope of the loss function. Points that way. And now we make an update of this term times 1, and we get 0. You can do the math. If you start from, you get 2. So you start from there, you do a gradient update of this with this step size. The next w you get is 2. And now the gradient points this way. You do an update, you get 0. And then, okay, well, let's do another update. And you get 2 again. And I think all of you can see at this point that this goes into an infinite loop of 0, 2, 0, 2, 0, 2, 0, 2, 0, 2, assuming the step size stays 1 forever. So it oscillates infinitely. Okay, that's bad. Let's try another step size, something really, really, really small. And this kind of animation I make is not to scale, but basically, if qualitative, what happens is, you start with 0, you want to make a gradient update, so negative in this direction, so towards this direction, but scaled by a very small number. So you go like this. And then you do another update. You compute the gradient again at this point, which is just a little bit to the right of the original point. You go look like this. You look like this. And of course, this is actually not animated to scale. At this step size, it actually looks a lot smaller than this, right? The changes are a lot smaller than this. So it takes a really, really, really long time. You can see that eventually it's going to get close to the optimal solution of minimal loss, but it's going to take a really, 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 really long time. So, I went into MATLAB, made a synthetic regression problem minimizing squared loss, and so this is what the loss curves look like in terms of number of iterations for different step sizes. So for really small step sizes, you see that it takes a long time to converge. As the step sizes get larger, it converges much faster. If your step size is too large, it diverges. And I should note that these numbers, depending on how you set up your learning problem, these numbers are not meaningful on an absolute scale. You should just think of their relative magnitude differences. And I'll touch on this point later. Okay, so what is the lesson here? The lesson here is that you want your step size to be as large as possible without being too large. Right? There's a sharp phase transition from when you're as large as possible to when you're too large. In one, you're optimizing this loss function super fast, and after a small number of iterations, you've converged something really close to the optimal solution. In the other one, you go off into oblivion. And it really does look like this for many, many, many optimization problems. I've suffered through this myself many times, where the loss function was just a little bit too, or excuse me, the step size was just a little bit too large, and then I run my gradient descent, I come back later in the day, and I get this model that's complete garbage because of this issue. Okay, so we'll talk about some tricks about how to achieve this sort of principle, but hopefully this principle is pretty intuitive. So now let's go back to talking about being scale invariant. So consider the following two gradient updates. So we have two loss functions, L and L hat, right? And suppose we're just optimizing, as a thought experiment, optimizing both, or one or the other. And the relationship between L hat and L is that L hat is just L times 1,000. So whatever L hat is that scaled by 1,000. So qualitatively, it's the exact same optimization problem. It's the exact same learning problem. The optimal solutions should be exactly the same. So ideally, we would want W to converge if we were to optimize our models for this versus optimized to this, we want W to have the exact same behavior, ideally, because they're essentially equivalent. They're exchangeable, these two loss functions. So if we want the learning procedure of these two gradient descent algorithms to yield the exact same sequence of models, how should the two step sizes be related? Any takers? Very simple answer.
Equal?
I'm sorry?
Must be equal?
They should not be equal. In fact, this guy should be the step size of the other one divided by 1,000. And the reason is as follows. Let's take the gradient. If this is, the gradient of this is exactly in the same direction as the gradient of this, times 1,000, right? So if we want to make the exact same sequence of updates, because we know this is just a scaling up of the other one, and we know that W's should, as in this simple thought experiment, should converge to the exact same solution. Then, if you want to enforce the same behavior, iteration after iteration after iteration, then the step size of this guy should actually be 1,000 times less than the step size of this guy. That's how you guarantee the same, exact same behavior. And that's why I say you shouldn't actually look at the absolute scale of these step sizes that I have here for this demonstration. If I scaled up my loss function up by 1,000, I would want to scale this down by 1,000 to achieve these exact same curves. Okay, so now that or any questions on this? Okay, so now given that, here's some practical rules of thumb. What I like to do, and you don't have to do this, but it's sort of pretty common in industry, and most people who do these type of things, is to sort of divide the loss function by the number of examples. So if n is the number of examples you have, and this is your loss function that sums over your entire training set, then you just divide by the number of examples. Once you divide by the number of examples, then how you reason about step sizes become more sort of comparable because they're sort of intuitively on the same scale. And then once you're optimizing, what I like to do is to start with a large step size, right? If you actually look at this curve, the large step size is actually doing the best until it starts diverging, right? So you start with a large step size, and as the loss plateaus or starts going up, or doesn't go down anymore, you do something like divide the step size by 2 or by 10. There's more advanced optimization methods you can use that's a little bit more rigorous and often could be a little bit more stable than this trick. And there's a recitation in a few weeks that will talk about that. But it should be noted that the step size must decrease over time in order to guarantee perfect convergence to the global optimum. Right. For any non-zero, for any non-converging, in the limit non-negligible step size, you can never perfectly converge to the global optimum with perfect precision. Okay, so when people do gradient descent, they often talk about convergence, right? And what does that mean? Convergence to what? And when many people analyze gradient descent, they do so in the context of convex functions, convex optimization functions. So what is convexity? Many of you probably have already seen convexity, but here's just an intuitive definition. What a convex function is, so this is f of x, the black line. A function f of x is convex if and only if you take 2 points, x1 and x2, and so f of x1 and f of x2, then for any point between x1 and x2, for any x between x1 and x2, f of x is less than the average of f of x1 and f of x2, right? So I could always pick any 2 points x1 and x2 and I draw a line between them, and the actual function between those two points is always below the line between those 2 points. That's the definition of a convex function. Right, so this function is not convex. In fact, it looks like my chicken scratch. One nice thing about convex functions is that it's easy to find the global optima because every local optimum, so every local dip in the function is guaranteed to be a global optimum for convex functions. And this inequality, so I say less than or this is less than or equal to, if a function is called strictly convex if this is always less than. A different definition of convexity can be done using gradients or derivatives. So a function is convex, and this is the equivalent definition, if and only if the linear extrapolation of a point x1, so here's f of x1, this is the slope at f of x1, this is the sort of the linear extrapolation at this point. So if I pretended I was always moving along the gradient at this point, it was completely linear, and this would be the linear extrapolation. So a convex function is always greater than or equal to its linear extrapolation at any point on that function.
Should that L be an F?
I'm sorry?
Should that L be an F?
Yes, I will fix that. Thanks. Actually, I think, right, because, okay, I apologize. So most of the community, when they talk about convex optimization, they treat the loss function as f. In this class, I'm mostly using f as the scoring function, and I use L as the loss function, so I confuse myself when I make this slide. So I'll fix this after class. Okay, so when you have a convex function, so this is also a convex function, all local optima are global optimum. So here we have a bunch of local optima. All of them have equal value in the objective. If a function is strictly convex, there's a unique global optimum. So here there's sort of an infinite range of global optimum. Gradient descent will always find the global optimum, assuming the step size is chosen safely. Almost all standard machine learning objectives that we talk about in supervised learning are strictly convex. Many of them are strictly convex, not all. We'll see some non-convex objectives in the second half of the course when we talk about embeddings and stuff like that in deep learning. Okay. So now let's talk about convergence in a little bit more formal way. So assume that our loss function is convex. How many iterations does it take to achieve a W whose loss is within epsilon of the optimal loss? If this property is satisfied, so for any 2 points A and B, the loss difference between A and B is less than or equal to the difference between A and B times some constant rho, for some fixed constant rho. This is called rho Lipschitz. If such a rho exists, then the number of iterations is on the order of 1 over epsilon squared. If the loss function is called rho smooth, in which case where the gradients of the loss function is rho Lipschitz, that's what rho smooth is, then you could converge in order 1 over epsilon iterations. And if the function is what's known as strongly convex, which just intuitively means something along the lines of it's lower bounded by a quadratic, then you converge in log over 1 over epsilon iterations. Recall that you want epsilon to be as small as possible, right? I want to converge to within 0.0001 of the optimal solution. Then the 1 over epsilon squared is much bigger than 1 over epsilon, which is much bigger than log of 1 over epsilon. So these are mathematical statements you can prove. These are big O. This is in big O notation, so these are all upper bounds on the convergence. And if you're interested in proving these things, you could read Sebastian Bubeck's optimization textbook, chapter 3. This is a free textbook. It's linked off my website. But I won't go over the analysis. These are just the types of convergence statements people can prove using mathematical tools. Yeah?
This is for gradient descent, not stochastic gradient descent.
It is actually going to also be true for stochastic gradient descent. Turns out, and I can point you to some technical references that prove it, but it turns out, I'll explain the intuition later by the end of this lecture. Yeah. It is also true for stochastic gradient descent. Right. So in general, of course, you want convergence, like true, strict, exact convergence when epsilon equals 0, but that's infinite, right? Like in general, it takes infinite time to reach the global minimum exactly, but of course, we don't really care about we're machine learning, everything's sort of kind of approximate anyways. we don't actually care about reaching the goal minimum. We just want to make sure that we've pretty much converged, right? Within 0.0001 of the global minimum. And so we want to be here. Generally don't care. And not here, right? But of course, when I plot this, this is like a retrospective reasoning, right? Retroactive reasoning. While you're running the algorithm, and you want to run it for as few iterations as possible, and be sure that you've mostly converged. How do you actually know that you're here and not here? Right? What does the curvature of the loss degradation look like? How can you tell? And this is a practical issue. I'm sorry, was there a comment or question? Okay. So, when to stop? Convergence analyses are worst case upper bounds, and they give you some handle and some intuition about how these algorithms perform. But they aren't always the most useful thing to do in practice, although they're often very useful. So now these are some rules of thumb that people in practice do in gradient descent. They stop when progress is sufficiently small. So you have actually computed, when you're at this point, you have actually computed the red curve all the way to here. You haven't computed the rest of it, but you have computed up to here. And so you just stop when progress is sufficiently small. I see that in the last 50 or 10 iterations, I haven't made much progress. I'm going to stop. Turns out that that's okay in convex optimization. Turns out that that's something that you can do and probably be close to the global optimum. You can stop after a pre-specified number of iterations, like 100,000, and then you can do early stopping. Stop when the validation error stops going down. I prefer this option most of the time. When I'm doing non-convex optimization, I prefer the third option. Okay, so limitation of gradient descent, and now we're going to segue into stochastic gradient descent, the last part of the lecture. So the biggest limitation of gradient descent is that it requires a full pass over the training data per iteration of gradient updates, right? In order to compute this gradient, I have to sum over every training example in my training set in order to compute this gradient, right? And this is extremely expensive when my training set is huge. If n, let's say n was, I don't know, 100 billion, right? It doesn't fit in main memory. So every time you do a gradient update, you have to page in data from hard drive multiple times. Like, you're just going to get screwed by the communication complexity. So a natural question to ask is, do we need to do a full pass over the data in order to make a gradient update? Right? If we don't, then that would save us a lot of computational savings. And that's where stochastic gradient descent comes in. So the intuition is as follows. Suppose the loss function that we're optimizing decomposes additively. And here we have a natural decomposition, one per training example, right? So we have this, I'm just going to call this L sub I, where this corresponds to the squared loss of the I training example. So our loss function decomposes additively. I'm going to normalize this for mathematical convenience. What that actually corresponds to, if you look at it, is this corresponds to the expectation over a uniform distribution over these subcomponents of my loss function, right? Okay. So the gradient of this guy is equal to the expected gradient of the subfunctions, right? If I just sort of take this interpretation and take the gradient, that's what it means. So what stochastic gradient descent does is it says, okay, well, it suffices to take a random gradient update. I don't need to take a deterministic gradient update. I can just take a random gradient update. Right? So long as my gradient update in expectation matches the correct gradient, then I'm good. It's a consistent update. So what does that mean in practice? It means at each iteration, I'm going to choose a training example at random, right? And then make a gradient update using that training example, just that training example, that one example. The expected value of this gradient update is the gradient update of the entire objective over the entire training set. Right, so this is in expectation consistent. And it turns out that because of that property, and you can prove that it also has the same convergence guarantees. Well, okay, that was I'll just leave it at that. Okay. So what does that mean? Well, that means stochastic. Oh, this is by the way, is stochastic gradient descent. This is it. It means that stochastic gradient descent is also an online learning algorithm, just like the Perceptron, right? It's a streaming algorithm. It takes in a stream of training examples. It does require that the stream is random, right? Whereas the Perceptron algorithm, the stream could be arbitrarily ordered. This needs to be randomly ordered. But beyond that, it is also an online learning algorithm. So you don't even need to have access to the training data, all of the training data up front. You could just have part of it at a time, and the stochastic gradient descent will work just fine. So what people actually do in practice is not just update one example at a time. They do what's called a mini batch SGD. So remember, batch learning is when you look at all the training data before you make a gradient update. Mini batch SGD is the following. I'm going to decompose this guy. Instead of being one subcomponent per data point, I get one subcomponent per batch of training examples. For example, 500 training examples or 1,000 training examples. And what this allows you to do is it allows you to do, in many cases, fast vector operations on 1,000 training examples using sort of fast matrix operations. Right? And this also decreases the volatility of your gradient updates because it's less random than it's still an expectation correct, and it has lower variance. Right? So this is actually the industry state of the art. Right? Everyone in practice basically uses mini batch SGD for some batch size. 500 is a good number. It's relatively robust to that. You could try 1,000. It doesn't make too big a difference typically. And you can often parallelize this. If you have a multi-core machine, different cores work on different mini batches, and they aggregate information. If you download any machine learning platform, chances are this is what's implemented in the gradient descent software.
Does it really matter a lot how I split it up into batches? If I choose 2 different allocations of batches, could I get completely different answers?
I don't understand.
So I think the idea here was I have some data, I'm going to split up into different batches and then do it separately on each batch. Does it matter how I split it up into batches?
If you split it up, as long as it's split up in a way that's random, if you have data sets large enough, it doesn't matter.
Okay.
Because you're going to converge.
Sure.
So the convergence guarantee says I'm going to be within some epsilon ball of the true solution, right? It doesn't make any more fine-grained statement than that, and somewhere within that epsilon ball. So if you do your batches differently, you may end up in a different point within that epsilon ball of the optimal solution, but you're guaranteed to be within an epsilon ball of the optimal solution. Yeah.
So with the stochastic gradient descent, you still need to, let's say, read a batch of 1,000, and it needs to be random. So you still need to read 1,000 random areas in memory. So I'm not sure I'm really seeing how this helps you to read from the hard drive list.
Right. So that's what you need to do to maintain the assumptions of the theoretical guarantees. In practice, what people do is they pre-shuffle the data, and then they just stream it in some arbitrary order. Right. And as long as this is a very fuzzy statement. As long as it looks random enough, it should just work. But if you want to do it, and mathematical analysis becomes very complicated, right? And when it's truly random, uniformly random, mathematical analysis is very clean. But in practice, the intuition is that as long as it looks kind of random, it's fine. Does that make sense? That's one of the sort of the tensions of teaching this class, right? I could teach it from a perspective of very clean math, but we'll never get to anything practical. Or I could just teach you practical things, in which case I explain things in very fuzzy ways. And I chose the latter, not the former, for the most part. Feel free to object to that in the course feedback at the end of the class if you want. Yeah.
So in the homework it says stop when the error is below a second point. Is that error like the one step, like the change per step, or?
I didn't write that specific part of the homework. The TAs wrote it, so I don't feel comfortable giving you an answer without looking at that question in detail. Is it posted on Piazza?
Oh,
Okay, if you post it on Piazza, I'll get a chance to actually look at the homework question in detail, and then I can give you, or the TAs can give you a more refined answer. Yeah.
You said the loss function is linear, but isn't it not?
I'm sorry?
Before you said the loss function is linearly separable.
The data set is, so in the Perceptron, I'm sorry.
Can you go back to the previous slide, like, before that?
Linearly decomposable,
Okay.
additively decomposable, which is which it trivially is.
Oh, okay, I see what you mean, okay. So
Yeah. So this is not separable. This is decomposable.
Okay.
So there's a different concept. One's a geometric concept. One's
yeah, I see.
okay. So checking for convergence, right? Remember when I said you check for convergence when it looks like your loss function isn't decreasing as that much. So the very fact of even plotting this curve required me to do a full pass over my training data for every point on this curve, right? Every point on this plot required me to do a full pass over training data. That's exactly what we're trying to avoid, right? And doing stochastic gradient descent. But we still need to do convergence checking to see if we should stop in stochastic gradient descent. But we don't want to actually computing this, right? Even computing this knowledge of whether or not just checking if we're good, not even doing updates, is too expensive. At least to do it every iteration. And if you do this every iteration, I guarantee you're going to lose all the speed benefit you get for stochastic gradient descent. It happened to work for this example because this example is a toy example that was So there's a few tricks. You don't have to check every iteration, right? I'm checking every iteration here. You can check every 1,000. You can check every 10,000. You don't actually have to evaluate on the entire training set or validation set if you're doing early stopping. You can do subsets of the training data, right? So for example, the previous 5,000 examples. I'm just going to evaluate my loss in the previous 5,000 examples. And in fact, this is what people often do in practice as well. And again, this in expectation will give you the right answer. So just a recap of stochastic gradient descent. Although, I should just mention for the homework, I don't believe you need to do this because the data set is small enough that you could just do something like this. Right? Okay, so just a recap of stochastic gradient descent. Conceptually, what it does is it makes this sort of conceptual assumption that the loss function decomposes additively into a bunch of subfunctions, and then subcomponents. You just choose one of those subcomponents at random every time you want to do a gradient update, and you do a gradient update on the gradient of that subcomponent. And in expectation, everything works out. The benefits is that you now avoid having to iterate over the entire data set for every update, right? And the gradient update is consistent in expectation, and then you have the same issues with step size and checking for stopping, but those are issues that you have to deal with in normal gradient descent anyways. And this is literally the industry standard with some parallelization and some mini batch optimization. So now let's come back to the perceptron algorithm in the last couple minutes. So remember one of the beefs I had with the perceptron algorithm at the beginning of this lecture was that it didn't seem like there was any objective function being optimized, right? Let's take a look at it again. So we have start with some initialization, we stream over the data, and maybe now we just assume the data is streamed in a random order, if that makes it easier to analyze. And then if we make a mistake, we do this. If we don't make a mistake, we just keep it the same. If we make a mistake, we do this. Is there some objective? Is there some loss function that we're optimizing implicitly?